q.com.
Welcome back to DDV Unit 1, Session 2. In Session 1, we have studied the lexical conventions. In Session 2, here we are going to study about the data types used in Verilog. What are the data types we are going to use in Verilog? We will study one by one. First one, the value set. Before that, what is data types? The data types is mainly used to declare something. Okay, in C programming, integer is one of the data type. By using the integer, we can declare the variables that store the integer values. Same way here in Verilog, so many data types are there. Okay, we will see one by one. Here, first one is a value set. It is a value set. So what are the value level used in our circuit? How it is declared in the Verilog programming? Generally, consider on logic gates. The logic gate consists of two states. One is set, another one is a reset. Okay, set means 0, set means 1, reset means 0. This is a general value used in any logic gates. Okay, so whatever may be the input, the output may be 0 or 1. This is a two-step. But in some circuits, it has two more values. One is unknown values, unknown logic value, that is also called as don't care. In K-map, we consider X, that is used as a don't care condition. Okay, so don't care means it may be 0 or it may be 1. Okay, we don't know the values, so it is called as don't care or unknown logic value, that is X. And another one value is high impedance value or floating state. Okay, so these four values are considered in a Verilog programming to represent the data. Okay, so let me see what is high impedance state. Consider this circuit consists of one PMOS transistor and NMOS transistor. These two transistors are derived by the logic gates, NAND gate, NOR gate and NOT gates. Okay, so one data input is given, another one is a enable signal is also given. Okay, based on the input signal, so the output is differs. So see the truth table in the right side. Initially the data and the enable both are 0. Then PMOS transistor and NMOS transistor both are switched off. At the time the output is a high impedance state, that is Z. Consider this circuit. This is a PMOS transistor. The first transistor is a PMOS transistor. This is a NMOS transistor. PMOS transistor is switched on for logic 0. NMOS transistor is switched on for logic 1. When this transistor is switched on, if the PMOS transistor is switched on, at the time the output is directly connected to the VCC. The output is logic 1. When the NMOS transistor is switched on, the output is directly connected to the ground. Okay, so at the time the output is a logic 0. Okay, both the transistors are switched off, so the output is not connected with VCC or not connected with the ground, so it is a disconnected. It is just like a open circuit, so it is a high impedance state, very high impedance state. Okay, right. Consider the second data, and the data is 0 and enable is 1. Then PMOS transistor switched off and the NMOS transistor switched on. So now the NMOS transistor switched on, so the output is directly connected to the ground, so the output is a logic 0. When the third input data is 1 and the enable is 0, then both the transistors switched off, so the output is again high impedance state Z. Then 1 1, the both PMOS transistor switched on, NMOS transistor switched off. So now the PMOS transistor connect the output to the VCC. So now the output is logic 1. Okay, so this is the different logic used here, but here X is not considered because X is the unknown value, but X is sometimes you are used in the flip-flops. Okay, right. And SR flip-flop or JK flip-flop, we are using the X value, so the X is the unknown value. Okay, right. Now next one, the strength levels. The strength level is also discussed with the voltage set and the value set. Okay, here some strength level is highest, strongest, some is a weakest. Okay, likewise they are differed. Okay, these are the strength. The supply represent VCC and ground, strong, pull, large, weak, medium, small, then high impedance, high Z. These are different strength levels used. So we will discuss later in deep. Okay, right. Next one, the first data type is nets. Generally, what is net? Net is the interconnection. Okay, consider internet. The internet connect the entire world. Okay, right. So here net represent the connection between hardware elements. Okay, just as in real circuit, net have value continuously driven on them by output of device that they are connected to. Okay, so nets means the wire. Generally, the wire. So in our logical circuit, consider one AND gate. The AND gate connect output is connected to the another one OR gate. So in between the AND gate and OR gate, we are using one wire to connect the AND gate or output to OR gate input. Okay. So here the AND gate is act as a driver. Okay, right. So the AND gate derive the wire. Okay. So the wire transfer the information from AND gate to OR gate. So this is a net. So this physical wire is considered in the programming by using the data type net. Okay, right. So the net may be a single bit or multiple bit. Okay, if it is single means it is represented as a scalar. So in the range specification is not considered. If the range specification is not considered, it is considered as a scalar. It is a single bit. Otherwise, we can change the number of bits by, based on the requirement. Okay, by using range specification. Okay, right. Then the default value of the net or wire is Z. Okay, high impedance state. The default value is high impedance state. Okay, except the tri-resist net, tri-reg net, which has the default value is X. Okay, the net get the output value of the drivers. Okay, if the net has no driver, it gets a value Z. Okay, so net should have a driver. Okay, without driver the net cannot do anything. So if the driver is not available, then the value of the net is Z. Okay, so that is a high impedance state. Default value is high impedance state. Okay, so net must need the driver. So net may be in scalar or in vector. Okay, right. Consider the example. First one, the wire A. Okay, wire A represent what? Consider the previous circuit. So this is an AND gate. B and C are input. A is the output. The wire A represent the output. Okay, the output wire. Okay, right. The output terminal of the AND gate is connected to some other gate by using a wire. That wire is represented as wire A. Second one is a wire B, C. So declare two wire B, C for the above circuit. So it is an input wire. Then consider another one wire D. Wire D equal to 1 bit. Okay, so the net D is fixed to the logic value 0 at the declaration. Okay, so it is a 1 bit length binary number. 0 is declared to the identifier D. Okay, right. Note that the net is not a keyword. Important point, net is not a keyword. Net is the data type. Okay, the net is represented by the wire. Okay, so the net has a different class of data types such as wire, then W and WR, then tri, then tri and tri-R, tri-register, etc. What is tri? Tri represent tri-state or three-state. So set, reset and high impedance state. Okay, the wire declaration is used most frequently. Okay, right. So most of the Verilog programming we use the wire only. Okay, so but the net data type having so many data type. Okay, so in that wire is the frequently used data type. Remaining wire and wire are tri, then tri and tri-R, then tri-register. These are the data types are used in the Verilog programming to declare something. Okay, right. Next we are going to see the registers. Registers used in the Verilog programming to store the values. Okay, right? The register represent the data storage elements. The register retain the value until another value placed on them. Okay, right? Do not confuse the register with Verilog hardware registers. Okay, consider one hardware register. It consists of n number of flip-flops and a clock. The clock may be synchronous and asynchronous. Okay, right? So this is a register. Okay, synchronous register and asynchronous register. So these register can store the binary numbers. So if the n bit register can store n bits of binary number. Okay, right? But here the register is entirely different. Here the register does not need any input clock. Okay, register is a data type. It can use it to hold the values, binary values. The register may be a scalar or it is in vector. The default value of the register is 32 bits. Okay, right? It is assigned by declared by the actually the register value is default. Okay, if the value is not assigned, it is defaultly considered as a 32 bit. Okay, right? Then the register data types are commonly declared by the keyword reg. Okay, the default value of the register data type is x. Okay, right? X. The example of 5 registers is shown. Next we are going to see the examples. Okay, right? Before that, the value of register can be changed anytime in the simulation by assigning new value to the register. Okay, right? So the register can store the data. Okay, right? It holds the data. We can change the data at any time. Okay, we can change the register size also. Okay, it is not fixed at 32 bit. So we can change the register data storing capacity by using the range specification. Okay, if the range specification is not mentioned, it is considered as a scalar. If the range specification is mentioned, it is considered as a vector. Okay, right. Next we see the examples. Consider reg register reset. Reset is the identifier, register is the keyword, then initial, then begin, then reset equal to 1 bit binary logic 1. Okay, the reset is equal to 1 logic 1. Okay, in the digital circuit. Then after that 100 hash 100 reset equal to 1 bit binary 0. Okay, so this program indicates the register keyword assigned to identifier reset. Okay, then after starting the program, initially the reset is assigned as 1 bit binary. Then after 100 time units, the reset value is 0. Okay, so here the reset is a identifier. It can identify the 1 bit length of data, because here the register is declared as a scalar, not as a vector. Okay, right? It is a single variable. It can store a single bit of data. Okay, consider the second one, the register signed 63S0 space M. Here the register is assigned with a signed 64 bit value, and another one is the register I. So the integer I, here this is a 32 bit signed value. Here the integer is not specified any range, so it is defaultly considered as a 32 bit value. Okay, then next one is a vector. Okay, so the net or register data type can be declared as a vector. Vector means multiple bit width. Okay, if the bit width is not specified, the default value is scalar, that is a 1 bit. Okay, consider the first example, wire A. So here the vector value is not considered, so it is act as a scalar, so it is a default length is 1 bit. Then second one, wire 7:0 bus. So the 7:0 is a length of the wire, so it can store the bit 8 bit. So the 8 bit bus, the wire is a act as a 8 bit bus. The next one is a wire 0 to 31. then bus A, bus B, bus C. Okay, 3 buses of 32-bit weight. Then wire clock is a scalar single bit. Then 0 is to 40 is a virtual address. The wire register virtual address of 41 bits. Okay, right. So here the wire can be declared at initially high is to low or low is to high, but the left number is the in the square bracket is always most significant bit of the vector. So here the wire 7 is to 0 means the 7 is the MSP, 0 is the LSP. Okay, right. Then the last one wire 0 is to 40. Here 0 is the MSP, 40 is the LSP. So the left one is the high. It should be high. It is a MSP and the right one is the LSP. Okay, right. So in the example shown above, the bit 0 is the most significant bit of the virtual address. Okay, right. So this is very important. So the left one is the MSP. Okay, right. Next one, the vector path select. So here the vector having n number of bits. So in the n number of bits we can choose any one range of the bits. That is called vector path select. Here for vector declaration, it is possible to address the bit or part of the vector. We can address the part of the vector or we can address a single bit of the vector. Consider the first example, bus brackets 7 bracket. Okay, this indicates the 7th bit of the bus A. So the 7th bit or the 7th of the vector bus A, that is considered, or the 7th bit is chosen. Then bus 2 is to 0. So here 3 least significant bits of vector bus. So 3 bits, last 3 bits, not last, least 3 bit. Okay, first 3 bit is considered in the second example. Okay, using bus 0 is 2, it is illegal. Okay, because the first one is a MSP, second one is a LSP. Okay, so if your reverse declaration is illegal because the significant bit should always be on the left of the range specification. The maximum significant bit should be always on the left side of the range specification. Okay, consider the address virtual address 0 to 1. So 2 most significant bits of vector virtual address. Okay, so these are the vector path select. So the vector having n number of bits, in that n number of bits we can choose any one of the bit. So that is called a vector path select, or any group of bits, it's a vector path select. Next one is a variable vector path select. The another ability to provide in Verilog HTL is to have a variable path select of the vector. This allows the path select to be put in the loops to select the various part of the vector. There are 2 special path select operators. One is path select increment from starting bit, another one is path select decrement from the starting bit. Okay, the format is starting bit plus colon width. Okay, starting bit minus colon width is a format of the variable path select. Okay, so the starting bit of the path select can be varied, but the width has to be constant. The width is constant. The following example shows the variable path select. Okay, consider the first example, register. Okay, then 255 is 0, then data 1. Okay, so the data 1 having 256 bits, then data 2 is that is also 256, but it is declared reversely. So when the MSP is 0, LSP is 255. That is considered as a big endian notation. The first one, data 1 is a 0 to 255, MSP is 255, LSP is 0. So it is considered little endian notation. Okay, right. Then another one is a byte is declared to 8-bit. Okay, 0 to 7, it is a 8-bit byte. Then next we are going to say variable path select. How we do the variable path select? First example, byte equal to data 1, 31 minus colon 8. Here 31 is a starting bit, minus represent decrement, then 8 is the constant. So we have to reduce the width from 31. Okay, so how much we have to reduce? The constant value is 8. So 31, 30, 29, 28, 26, 25 and 24. So totally 8 values. The width is 8. From 31 to 24 is the correct data specification. Okay, so the width is 8, the starting bit is 31. So we are going to reduce the starting bit, the width, by using 8, the constant. Okay, from starting bit, that starting bit is 31. So 31 minus 8, okay, that is a 24 along with 31. Okay, similarly second example, 24 plus 8. Here the 24 is a starting bit, then width is the 8, then here the plus is increase considered, that is its increment. So the starting bit is 24, so 24 is in the right side. Okay, then 31, 24 plus 8 along with 24, so that is called 31. So the MSP is a 31, LSP is a 24. Then consider third example, that is from data 2. The data 2 is declared as a big Indian notation, so it just opposite. So this 31 minus 8, the constant is 8, so 31 is a starting bit, then width is 8, then the data width is 24 is to 31. Okay, just opposite to the first example. Similarly the fourth example, 24 plus 8, starting bit is 24, width is 8, then the data is 24 is 31. Okay, so this is a big Indian notation. Okay, the starting bit can also be variable, the width has to be constant, therefore one can use the variable part select in loop to select all bytes of the vector. Okay, consider using one for loop for j equal to 0, j is less than or equal to 31, then j equal to j plus 1. This is a loop. Then byte equal to data 1, okay, into j into 8 plus 8. If j equal to 0, okay, what will happen? The starting bit is 0. Okay, then increment plus, then 8, then 0 to 7. Okay, the sequence is 0 to 7. If it is 1 means 8 to 15, because the starting bit is 8. Okay, 8 to 15. If it is 2 means starting bit is 16, then 16 to 31, like that. Okay, so similar way we have to write the different sequence based on the j value. Okay, right. Can initialize the part of the vector. So consider the next example, data 1, the byte number into 8 plus 8. Here 8 binary, that is equal to 8 bit binary 0. If the byte number equal to 1, then it clear 8 bit, so it shows 8 is to 15. Okay, the starting bit is 8, in the MSP is 15. Okay, so this way we can select the different part of the vector. Okay, next one we are going to see the integer, and integer is a general purpose registered data type used to manipulating quantities. Integer are declared by the keyword integer. Although it is possible to use register as a general purpose variable, it is more convenient to declare integer variable for the purpose of such as counting. Okay, the default width of the integer is machine word size, which is implementation specific, but at least the integer size should be 32. Okay, the register declared as a data type, register store then value as unsigned quantities, whereas the register store value as signed quantities. The register store the unsigned quantities, but the integer can store signed quantities. Consider the example, integer and counter. Counter is an identifier, integer is a data type. then initial counter equal to 1. Here the negative 1 is assigned to the counter 1. The counter is declared as a integer. Okay, so integer can store negative number, so it can store the signed number. Okay, next one is a real number constant and a real register data type are declared with the keyword real. They can be specified in decimal notation, example 3.14, or in scientific notation, example 3e⁻6, like that. Okay, right? The real number cannot have range declaration, so it is a scalar, and their default value is 0. The real number default value is 0. When the real value is assigned to an integer, the real number round off to the nearest integer. That is an important point. Okay, right? The real is a constant or real data register, okay, declared with the keyword real. So it can be specified. It can be used to specify the decimal notation or in scientific notation. The real number cannot have the range declaration. That is an important point. Okay, see the example. Consider the first one, the real delta. Okay, the delta is the identifier. It is declared by the real. Okay, then consider the begin, then delta equal to 4e⁻10, then delta equal to 2⁻13. That is the end. So the delta value is declared, okay, right, by using a scientific notation and the decimal notation. After that, we consider the integer 1i. The I is the identifier that is declared by the integer. Then initial I equal to delta. Here delta, the last delta value is 2.13. okay, 2.13. So the 2.13 is round off to 2, then the I value equal to 2 after the execution, because here the I is declared in the integer. Okay, if the I is not declared by the integer, means the I value will be 2.13, but here it is declared through the integer, so it is 2, because the real number is round off to the nearest integer value. Okay, right. Next one is time or simulation time. The Verilog simulation is done with respect to simulation time. A special time register data type is used in Verilog to store the simulation time. A time variable is declared with the keyword time. The width of the time register data type is implementation specific, but it is a 64-bit. So up to this time, many data types are studied. The default value of their data types are maximum it is a 32-bit, at least 32-bit. But the first time here, the time the data type value is 64 bits. The system function $time is invoked to get the current simulation time. Here the dollar symbol is used. The dollar symbol indicates the system function. Consider the declaration, the time. Time is a keyword. Okay, then save simulation time. Save sim time is a identifier, the initial, then that identifier equal to $time. So this indicates, so the $time is a keyword that is used to store the simulation time in the variable save simulation time. Okay, right. So this way we can find the simulation time of our Verilog programming. Okay, then next one is the arrays. Okay, so as like in a C program, here the arrays are used for register, integer, time, real time, and vector. Okay, register data types. The multi-dimensional arrays can also be declared with any number of dimensions. Okay, arrays of net also be used to connect port of general instance. Each element of array can be used in the same fashion as scalar or vector net. Arrays are accessed by array name, then subscript. For multi-dimensional arrays, the index needed to be provided for each dimension. Okay, consider the examples. So array is mainly used to store the different numbers of same dimension. Okay, declare with any number of dimension. Okay, array net can also be used to connect port of the general instance. Okay, net is also used as arrays, register is also used as arrays to store the different bits. Okay, multiple bits. So consider the first example, integer. So count 0 to 7. Here 0 to 7 represent the count number. It is not a 8-bit. Okay, count number. So here an array of 8 count variable that is stored in integer. The array of 8 count variable. So integer value in the range is not specified, so it can be considered as 32-bit. Okay, then second one, the register bool represent the boolean. Okay, so 0 to 31. Here 32 1-bit boolean register variable. 32 1-bit boolean register variable. Okay, the bool 31 is 0 represent 32 count. This is also represent the count. 32 number of boolean variable are stored in the register. The register can store a 1-bit number. It is not a multiple bit. Register can store 1 bit because it has no range specification. Next one is the time check point. 1 is 100. Here also the time is a keyword. Checkpoint is a identifier or variable. So here array of 100 time checkpoint variable. Total number of checkpoint is 100. Then register 4 is to 0, port id 0 is to 7. Here two ranges are specified. First, register range. So register range indicate number of bits. Number of bits it can store. 0 is to 4 means it is a 5 bits capacity. The register can store 5-bit capacity, and the port id is 0 is to 7. So that indicates it has a 8 number of port. Okay, 8 number of port. The array of 8 port IDs. Each port ID is 5-bit length. Okay, right. Next one is a integer matrix. So it is a multi-dimensional or a 2-dimensional matrix. It is defined by two different ranges. One is 4 is to 0 and another 0 is to 255. 4 is the start bit and 0 is the end bit. Here 0 is the start bit, 255 is the end bit. Okay, right. It is a multi-dimensional array. Then another is a integer matrix, array same. Then register 0 is to 63. That means this register can hold 64-bit. Then array of 4-dimensional. Okay, 4-dimensional array. Then wire 7 is to 0. Then wire array to 0 is to 5. Here it is a 6 number of 8-bit data can be stored. Okay, 6 number of 8-bit data can be stored in the given wire. Then wire array 7 is to 0, 5 is to 0. That is a 2-dimensional wire declaration. Okay, right. It is important not to confuse array with net or register vectors. A vector is a single element that is n-bit wide. On the other hand, the array are multiple elements that are 1-bit or n-bit wide. Okay, so do not confuse the net declaration along with the wire declaration. Okay, right. Then examples of assignment to elements of arrays discussed above in shown figure. So count 5 equal to 0. Here what is that? Reset 5th element of the array of count variable. Okay, so 5th element, okay, this considers 0. Then checkpoint 100 equal to 0. Reset 100th time checkpoint value. Then port ID 483 equal to 0. So reset 3rd element. Okay, a 5-bit variable. Okay, 3rd element of the port ID is equal to 0. Then matrix 1 0 equal to 33559. Set value of element indexed by the matrix 1 0 to 33559. Then array 4-dimensional 4D 0 0 0. Then 15 is to 1, that is equal to 0 means clear bits 15 is to 1 of register accessed by the 4-dimensional array 0 0 0. Okay, then port ID equal to 0. So it's a illegal syntax here. Attempt to write the entire array. Here array is not mentioned directly. The array name is given, so it is a illegal syntax. And the next one is a memory declaration. In digital circuits, we are using memories. Okay, the memories are RAM and ROM. The RAM and the ROM store the binary data in the form of row and columns. For example, if it is a 1 kilobytes, so that indicates 1024 number of 8-bit data can be stored by the particular register. Okay, so 1 kilobytes means bytes means 8-bit. So 1k represent 1024, that means 1024 into 8 bits. Okay, the particular memory can store 1024 of 8-bit numbers. Okay, same way here the memories are represented by using array. Okay, the memories are considered in the register. Okay, each element of the array is known as element or word is addressed by the single array index. Each word can be one or more bits. Okay, it is important to differentiate between n 1-bit register and 1 n-bit register. N number of 1-bit register and 1 number of n-bit register. This particular word memory is updated by using address as a memory array subscript. Consider the first example, register memory bit 023. So this instruction, this register can store 1024 number of 1-bit data. Okay, memory 1-bit memory data. Okay, 1k of 1-bit memory. Second one, register 0-7 memory byte of 0-1023. So here 1 kilobytes. This instruction represent 1 kilobytes. So the Verilog can store 1024 number of 8-bit data that is stored by the register. And the memory byte is 511. That indicates the fetches 1 byte word, those address is 511. Okay, the address is directly given by the memory byte. Okay, next one is a parameter. So the parameter is mainly used to declare the constant in the Verilog programming. Parameter cannot be used as a variable. Parameter values for each module instance can be overwritten, okay, individually at compiling time. This allows the module instance to be customized. This aspect is discussed later. The parameter type and size can also be defined. Okay, right? So the parameter is a keyword we cannot use as an identifier. Okay, right? So parameter cannot be used as a variable. Okay, right? So the constants are declared by using the parameter keyword. Okay, parameter is a keyword, then port ID is the identifier, that is equal to 5. So defines the constant 5 is declared to port ID. Similarly, parameter catch line width is equal to 256 means constant defines the width of catch line. Okay, then parameter signed 0 to 15 width. Pixel sign and the range of parameter is width. Okay, right? So this way we can define the constant in the parameter by, okay, we can declare the constant in the Verilog programming by using parameter. And the last one is string. Okay, string can be stored in the register. In Verilog programming we can display the strings in output, okay, by using the register keyword. Okay, in string declaration the register must the register capability must be greater than the string number of strings. In the string, each letter is represented by the 8-bit data. Okay, each character is considered as a 8-bit data. Okay, if the width of the register is greater than the size of the string, the Verilog fills bits to the left of the string with zeros. If the register width is smaller than the string width, the Verilog truncate the leftmost bits of the string. It is always safe to declare the string that is slightly wider than it necessary. Okay, so consider one string, hello Verilog world. Here total is 17 characters are there. Okay, 5, then 7, again 5, Okay, totally 17 characters are there, but here instead of 17, 18 is mentioned. Okay, each character can represented by 8-bit number. So the register capability is 8 into 17 is to 1. Oh sorry, it is considered, actually it is start from 1. Okay, it is start from 1, it is correct. Totally 17 correct. If it is start from 0 means 0 to 17 into 8 bit. Okay, and otherwise you can multiply 17 into 8 and put the value around 136, I think. Okay, so 0 to 135 likewise we can declare, or 1 to 136 we can declare, or 1 to 8 star 18 is also we can declare. Okay, so string value, the string value is assigned to the register with range. Okay, after that the string value equal to hello Verilog word, that is our string that is defined in the double quotation. Okay, the special characters serve the special purpose in displaying the string, such as new line, tabs, and displaying argument values. The special character is displayed in the next slide. These are the some special characters along with the escaped characters. Then character displayed. If slash n represent the new line, slash t represent the tab, then percentage it is character displayed as percentage, then double slash is considered as single slash. Okay, then quotation and character within a octal digits. Okay, so these are the different special character used with the strings. Okay, right. So in this session we have studied the data types used in the Verilog programming. Okay, so all the data types are important. So the data types along with the examples we have studied. In the second unit we will use these data types to write the program. Okay, right, or the first unit end also we will see some program. Okay, right. So thank you, thanks for watching.